Morning again. Last time we were talking about RLT circuits, resistor transistor logic circuits, and we analyze the circuits first, and then we look at how we can shift the transfer function, for example, by putting two more diodes, but in normal operation we analyze it without those two diodes, and then we have seen how we can implement NOR circuit and also AND circuit. So these are like two input ANDs. If we want three input AND, we can put three of them on top of each other. That was the case. So another important point that we will be analyzing for the logic circuits is the fan-out, like how many gates we can connect at the output. Okay, so this needs to be calculated, and we need to have an idea, like why or how this should be determined. So for these circuits, when we connect to each other, we need to look at for two cases. For the output, like this output high case and output low case. Okay, so that's going to be the cases that we need to analyze. So for the output, like this V output, for two cases we need to check how many we can connect, and the minimum will be the maximum we can connect. So minimum of the two, output high and output low case, and then that's going to be maximum we can connect. So for output low case, we need to understand and analyze this thing. So this is one gate, of course, this is one gate, and then this is the second gate, and then this is the two gates that are connected here. So the idea is, like, when we connect one, so there might be one more and one more, and then okay. So is there a limit of connecting for output low case? So when we say output low case, we are talking about this V out. Okay, of course there are outputs also here and outputs here, but that's the next gate. So for output low case, how does it occur? Output low occurs when Vin is high. When Vin is equal to let's say 5 volts. Okay, then we know that Q transistor Q is what? In saturation. Since it is in saturation, we know that output voltage V out is going to be equal to the collector emitter SAT voltage, which is 0.2 volt. Okay, so for 0.2 volts, what is the state of next state? If that's the case, Q AX is equal to, what is the state of this?
Off.
Is cutoff, right? Off. Okay, so therefore, is there any current coming from here? We call this thing I in, I input low or I in prime. Okay, if that's the case, I in prime is equal to 0. So there is no current coming or going to the first stage. So driving stage. This is the driving. Okay, or driving gate. So if we connect, like, many gates here, it's going to be okay. So since QAX is going to be 0, so let's call this thing V out of X. Okay, if that's the case, V out of X is going to be equal to what?
VCC.
It's going to be VCC. Okay, so low here gives us high here, right? So therefore it's okay. Okay, so for this case, what is going to be maximum and low maximum? How many we can connect? There is no limit, basically. We can say it's infinity. And it will work, right? I mean, if we connect 100 of them, again, all the hundreds are going to give you high. This will be high, this will be high, and all of them are going to be high. We out of X, okay? So there is no limit. Okay. So it's good. It's good. No problem here. The problem is for the output high case. What happens for the output high case? So that's the thing that we need to analyze. For output high case, this is our transistor. It's going to be off, right? This is off. That's the output high case. So, but when you connect the next gates, so this is high, this is going to be high. If this is high, output here, the next gate needs to be, let's say this is V out X. Okay, needs to be what? Low. Okay, so and then ideally, or what we want is this value to be 0.2 volt. In fact, if this is the next stage is up to 0.7, this output will be connected to another inverter, so it should be okay, like up to 0.7 volts, because this output, if it is connected to another inverter, okay, another inverter, up to 0.7, nothing changes. But still, as a convention or convenience way, we don't look at this. I mean, we don't look at this point to be up to 0.7. We say it should be 0.2, and then it should remain at 0.2 in the worst case. Okay. So for the worst case, this needs to be remaining at 0.2, this value, this output value. Okay. So now, but if we connect a gate here, something here, this next gate, output here is not going to be 5 volts. Okay, so if n is equal to 0, Okay, that means nothing is connected. V out is going to be VCC. Okay, but if n is equal to 1, then there's going to be this IN prime current. So therefore, V out will be less than VCC. How much less? When we say V out, we are talking about this V out. Okay, how much less? We don't know. I mean, but it's going to be for sure less. I mean, this is going to be how much less? We can say that it's going to be V out. Maybe I should, draw it this way. V out is going to be VCC. This time V out is going to be VCC minus IN prime times RC. So it will be less than VCC. Okay. So if n, this value is going to be V out minus is going to VCC minus n times IN prime times RC. Okay. So V out keeps dropping. For this gate, maybe I should use a different color here. Okay. For this gate, we want this to be in saturation output. So see, it is a similar gate to this one, but the transfer function, remember, was like this. It used to be like this. I mean, it is like this. So this is V in, this is V out. So let me put this V in X and V in V out X, which is same as the first stage, but just to declare that it is the case here. So this is V input high, and then this is VCC originally, right? So the voltage, the input voltage, this V in could be VCC, and output is going to be 0.2 volt. If here we apply directly VCC, it's going to be, output is going to be 0.2 volt. Okay. So if we apply here less than that, maybe another value, like this value, or this value, or this value, okay, still it's going to be, output is going to be 0.2. So output means this one, 0.2. All right, okay. So what is the minimum drop that we can tolerate here, so that still output is going to be 0.2 volt? How small we can allow this?
V input high.
I need to V input high. Great. Yes, you're right. So minimum value of V out, it can be V input high. Okay. So V out minimum is going to be V input high. Okay. So if nothing else is defined. So if that's the case, then we can find here I out. Okay, I out. So for that minimum, what is I out? VCC minus V input high divided by RC. Okay. So that's I out. What about for this case, I in prime? What is Y in prime? We input high minus what? 0.8 volts divided by R Bx. Okay. So that is what is needed by the next gate so that it will be still in saturation to keep V out X to be 0.2 volts. That's the edge value. So therefore N, this time high, max is going to be I out divided by I in prime. Okay. So that's how we find maximum number of gates. So and max should be less than or equal to, okay, or n max is this, okay. So if you find this n max to be, let's say 5.8, that means nh max is equal to 5, because if you use 6, then this is not going to be satisfied. Is that okay? I need a feedback from you.
Yes.
Yes.
Okay. Okay. So one thing that sometimes, you know, we give this criteria to be a little bit different than this. Okay. If you know, if nothing is defined, V out min is V input high. Okay. But sometimes, you know, we say that we want some tolerance here, noise margin. So noise margin high required. If that value is entered here, then you should be using that value here instead of the input high. Okay. In some cases, you know, the designer says that, okay, I don't want to go down to the input high, just, you know, to be in the safe region. I want 1 volt larger than that. Okay. Noise margin high required is defined. Then instead of we input high, sorry, we input high needs to be changed with we input high plus noise margin high. Okay. So this will be V out minimum. Is that okay?
Yes.
Okay. So in the, you know, previous year's exam questions, you will be seeing that it will be asking you what is the fan out of this circuit if noise margin high needs to be larger than 1 volt, you know. So then you say, okay, I need to add that value to determine V out min. Okay. So there are a lot of example questions, you know, in the last year's exams for these things. So you will be seeing that. So you know, the minimum here we say can be down here, and I don't want to you know, elaborate it anymore, but you know, somebody can argue that, yeah, I don't have to go down to 0.2. 0.7 is also okay because the next gate is going to be still off. But you know, we do it this way. Okay, so this is kind of the convention. We say it should be in SAT. So this one is supposed to be SAT. So that's how we calculate the numbers. Okay. So another subject is the power dissipation. So the power dissipation, oh, by the way, here we need to also maybe say talk about N max. And max is the minimum of N low max and N high max. Of course, here it's going to be equal to the limiting one is going to be N high max because this one is infinity. Okay. So you know, there are different ways of calculating this. Some people do it. Maybe I should write it down. Also, one other thing here. Some people, in order to calculate this V out midpoint, they do this. So they say that this current V out is going to be VCC minus V out divided by RC. How do they do that? They say that this current is, you know, n times of that happens there. So they calculate it from a different point, but that's very confusing. So don't, I would say, I don't recommend that to you. But how can I write that here? So writing this is equal to n times V out minus 0.8 divided by R bx, and then saying that, you know, find V out is equal to blah 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 blah, and then that should be equal to you know, V input high. So this method is not so good. Okay. You know, don't use this. Use just find I out first, and then find V in high separately, and divide those two to each other. And because that's also good for these kind of cases, noise margin high added cases. Okay, so there are two methods here. One, to write all the currents and then, you know, find the value of V out and then say V out is I input I, but that's not a good method, okay? Do not use this approach. So I guess if you look at last year's exam questions and the solutions, you will understand what I mean. But what I explained is the better way of doing it. Okay, so one other thing we need to determine is the power consumption. Here, the power consumption is going to be determined by VCC times ICC. Okay, so but there might be also current coming to this transistor from Vin. We don't account that here because, you know, gates are going to be connected to another one and another one and another one. So eventually, what we really care is the power that goes through VCC. Okay, so VCC. So, you know, these currents, we really do not care because these currents will be coming from here anyway. So therefore, only ICC is looked at. Okay. So currents coming from previous gates are considered in the power dissipation power of the previous case, previous of the okay. So we only need to calculate ICC and VCC. So of course, VCC times ICC is going to be the power consumption, but we know that output, you know, can be high or low. So in the circuit, maybe 80% of the time output is high, 20% output is going to be low. But you know, that creates unknowns. We will assume that half of the time the output is going to be high and half of the time it's going to be low. So we will be determining an average power consumption for output low case. So for this one now, we also notice that if there is something here, there might be some extra currents here. But so therefore, when we want to calculate the output, I mean power consumption of a gate, we can do it for no load case or if there are any load. So let's look at the no load case. If in the exam we say that find the average power consumption, you can do it no load case, but if you want, you can say, okay, I assumed it's driving one gate, so I calculated accordingly, okay? But typically we tell you, find the power consumption if this gate is driving two similar gates, for example, then you need to calculate accordingly. Now for output low case, we can find the power dissipation. We know that this QA is what? What is the state of QA?
Saturation.
It's in SAT, okay. QA in SAT. So therefore, ICC is going to be equal to IC, which is equal to transistor collector current. And that's going to be equal to 5 minus 0.2 divided by RC. Okay. So this is, of course, VCC. This value is V collector emitter SAT voltage. Okay. So what is the power dissipation? Power dissipation for output low case is going to be VCC times ICC, which is, you can calculate and rewrite this thing. I mean, it's going to be VCC times VCC minus VCE SAT divided by RC. Okay. So what about output high case? If there is no load, QA in
Cutoff.
cutoff. If that is cutoff, what about ICC, which is equal to IC, which is equal to 0? Okay. So what is P output high case? VCC times ICC, which is equal to 0. Okay. So P average is going to be P output high plus P output low divided by 2. So it's going to be equal to, in fact, P output low divided by 2. Okay, so that's how we calculate the power dissipation. Very simple. 50%, 50% high, and then 50% of the time it's going to be assumed low. This is the assumption, okay, of the time. Okay, so that's how we calculate. If we have more gates, like we don't know, AND gates, it's driving AND gates, then we need to calculate for output low case, it's the same. Okay, because no current is coming here. This is 0.2 volts, and then I in prime times N is equal to 0. So it's same. So P output low is going to be equal to VCC times VCC minus 0.2 volts divided by RC. Okay, but output high case depends on the N, the load. Okay, so here is the way that I was telling you, not use the not find the fan out. So some people just do this, like, if there are so many of them, so they will be coming in parallel, so these are all the next gates. Okay, so maybe I should do this. Okay, next gate. Of course, the next gate has some other components here, right? I mean, we know that, but we don't really care about those, RCX, VCC. So we ignore that. And this is 0.2 volt, and then this is 0.8 volt. So this is the next gate, okay? So we can find the current this ICC from this circuit here. So P output high is going to be equal to VCC times current. So this current, we can say that I out or ICC, and ICC is going to be equal to I out, and then that can be determined from here. If there are n of them, you know, we can make the this representation. Okay, so this model, this thing models the circuit here. So therefore, VCC minus 0.8 volts divided by RC plus RBX divided by N is going to give us ICC. Okay. So, so this is good. Let me ICC, but using this model, to determine Nmax is confusing. Okay, just as a note for you. Okay, some people, you know, use this model and then determine this and then say that this should be less than V output high. Sorry, or V input high, you know, for the fan out. Remember, we said that this should be less than V input high. So we can use this model also here, but don't use it. I mean, use the method that I suggested. Okay, so here we find V output low, V output high, and then we still take the average. You know, we can say that eventually P average is equal to P output low plus P output high divided by 2, 50% usage. Is that okay? So this is next gate 1, next gate 2. Questions? I guess this is kind of repetition and load case, okay? If n is not given in the question, you can assume it to be 0, no load case, or assume it to be 1. Okay. Please state your assumption. In the solution. But typically we should give you like, what is going to be the n. Of course, assuming it's 0 will be easier for you to calculate. So, but if you want to show that you really know what you are doing, assuming it to be 1, of course, gives a better maybe impression of your knowledge. Okay, so this was the RTL. So in a summary, in the RTL, the output is not rail to rail. So what is rail to rail? I guess it's clear. So it's between V out is between VCC and something larger than 0 volts, okay, 0.2. So V output low is 0.2 volt. So not down to the ground rail. Okay, so positive one is okay. This is okay. This is good. But the other one is not good. So, but it's not bad. I mean, 0.2 volts, it is still good value. V out is between 5 volt and 0.2 volt. Not bad, I mean. So it's good. So static power consumption is not equal to 0. For output low case, it is 0. But sorry. For output high case, no load. Okay, it's confusing. Let me just erase this. Okay. Output low case, there is power dissipation. Output high case, there is power dissipation. If n is not equal to 0. Okay. So another thing is transition is not sharp. As you notice, it's coming like this and it's going like that. Oops. Okay, V in, V out. And then noise margin high is not equal to noise margin low. So maybe can be this value is 0.7. Remember, this is 0.2. So noise margin low is 0.7 minus 0.2, which is 0.5. It's very low. Can be improved by adding diodes next to to RB. And output high is limiting maximum fan out. To solve this, DTL can be used. DTL is diode transistor logic. And then we will be looking at this now. Okay, I'm recording it. Okay, that's good. Okay, so that's the next logic we will look at. Diode transistor logic. Is that okay? Any questions? So if not, I'm suggesting to give the break here on time before we go to DTL. Is that okay?
Yes.
So let me go here, and then we are recording, so I pause. Okay, so let's go to the next gate, diode transistor logic. When people saw the drawbacks of RTL, they came up with another logic circuit like this. Okay, so this logic here, we will be obtaining voltage transfer characteristic of this device by looking at the extreme cases. Okay, so let me go to next page first, and then
Hocam ekranı
find what.
paylaşmadınız galiba.
Oh, sorry. It's good. Okay. So this is the circuit, diode transistor logic circuit. Here we will obtain voltage transfer characteristics. So what happens if Vin is 0, and then where does the change occur the first time, and then when does this other case occur? So this is going to be defined as V input low. This is going to be defined as V input high. Okay, so the cases are drawn here. What happens if Vin is equal to 0 volt? Okay, so that's one extreme. So we expect output to be high, right? So that's the idea. So if Vin is 0 volt, we know that there's a current path here. So then we know that dA is what? What is the state?
On.
dA is on, yes. So if dA is on, let's call this voltage Vx. Maybe I should change the color of the pen. So this voltage is Vx. Okay. What is Vx? What is Vx voltage?
0.7.
Or diode? What? Sorry.
0.7.
Yes, 0.7, because we say that when the diode is on, it's 0.7. So you know that normally diode, is defined like this, but then our assumption is that diode is behaving like this, 0.7, right? So this is V diode, I diode. Okay, the model that we use. So if that is 0.7, this voltage is 0.7 volts. What about this diode and this diode? Is 0.7 enough to turn on both junctions?
No.
Okay. So we cannot say that one of them is on, the other one is off, because one of them is off means current is 0. So dB and base emitter of Qn are off. Okay, because 0.7 is not enough. To turn on both junctions. Okay, and if that's the case, what is this current? I base. I base
Zero.
is, okay, so if I base is 0, then we know that Qn is in cutoff. Does it make sense? So no base current. Current can only go in this direction, and no base current, and then so that junction is not turning on, it's not forward active, and this is typically is going to be off anyway. And this cannot turn on also. So both junctions are off, therefore Qn is cutoff. If Qn is in cutoff, what is V out?
VCC.
Yep. VCC, that's it, VCC. So what is this value? How do we call this value? V output high. Okay, so when we come back to this drawing, here, this is VCC, and that's where it starts. And then we call this thing V output high. Makes sense, right? So this is not complicated. So this will remain here until when? V out will remain at VCC as long as what? dB and phase emitter of Qn are off. Okay. So if Vn is equal to 0, we know that Vx is equal to 0.7, which is less than what? Voltage of dB plus V base emitter of well, let me just say here 2 times 0.7 plus 0.7. okay, which is 1.4 volt. So if Vin is equal to 0.2 volt, Vx is equal to 0.9 volt, which is less than 1.4 volt. If Vin is equal to 0.5 volt, then this will be 1.2 volt, which is less than 1.4 volts. Okay, so when Vin is 0.7 volt, Vx is equal to 1.4 volts, which is equal to 1.4 volts. So Qn dB and Qn starts turning on. Okay. So when Qn, slide current starts going through here, then slide beta times of that slide current is going to be coming from RC. So therefore output will start decreasing. So that's the break point. So until here, which is not shown to the scale, but onto here, input 0.7 volts, nothing will change. Okay. So nothing will change until that. What happens if the input is 0.71? Okay. So Vn is between 0.8 and 0.7 is the interesting point. So it is not really coinciding with our model Vx. So if Vn is 0.71, okay, so there's going to be current here, and then this current will start dropping here. So the transistor goes from maybe forward active, it will be, till it goes to saturation. So there's going to be a very sharp increase here. So, here, 7.2, blah, blah. And then when it reaches to 0.8 Vn, we know that it goes to Qn is sat. Okay, Qn is sat means V out, it becomes 0.2 volt. So here, 0.70, transistor Qn was off or forward active. So in here, it's actually in forward active. The model is not maybe showing this precisely, but it's the same thing like when we say the diode here, like the diode, model is like that, but actually it's like this, right? So in the transition case, voltage of the transistor goes from forward active to saturation very fast. In summary, when Vn becomes 0.8 volt, basically 0.8 volt, then this is 1.5 volt, then this becomes here 0.7 volt, this junction becomes 0.8 volt, and then Qn goes to SAT. Okay, so here that means from here to here there's going to be a very sharp transition. So when this goes to 0.2 and becomes SAT, this is 0.8. So in fact, we calculated, we output low, and also we input high. We both determined we input high and we output low. Is that clear?
Hocam bir output low'u nasıl bulduk? Onu kaçırdım sanırım.
Now, you know, this is the formal thing is like, this is 0.7, this is 1.4 volt, and then this is 0.7 volt, right? I mean, that's the edge of forward active, and output is VCC. So when you start, you know, applying here, 0.71, this becomes 1.41, and then this becomes like here, not 0.7 anymore. As you know, base emitter voltage determines IC, right? What is IC normally? IS, e to power V, base emitter divided by VT, right? I mean, there's -1, but we can ignore that. So here, when base emitter is becoming larger than 0.7, IC starts increasing, right? So we say in the model, this is either 4.7 or, you know, when it's forward active, or 0.8 when it's in SAT, but there's a transition. And during that transition, that IC increases, and IC increases, that means the voltage decreases here. And then when this voltage becomes 0.8, that base emitter voltage, then output or QN becomes SAT. So when QN becomes SAT, that means output is going to be 0.2 volt.
Okay, thank you.
Okay. So this transition happens very sharp, you know, it's not maybe to the scale here. So if we keep increasing the voltage here, what happens? If Vin, maybe that's the third case, if Vin is larger than 0.8 volt, okay? So if Vin is larger than 0.8 volt, what is Vx? Can Vx be, let's say Vn is equal to 0.9, okay? Nine volt. So what is Vx? We know that now this is in saturation. So this is 0.8 volt, and then this is 0.7 volt. Therefore, Vx is 1.5 volt. Okay. So this is going to be fixed to 1.5 volt. And if this one is 0.9, then dA becomes off. Okay. So Vn is, let's say, 2 volt. Vx still 1.5 volt. dA is off. Vin is 5 volt. Vx will remain maximum of 1.8 volt. And dA is off. Okay. So notice that input is 5 volt. dA is off. What is this current? That current becomes 0. Remember, V output high, for the V output high case, the next gate, if there's a next gate here, is I in prime. Maybe I shouldn't have drawn here, but not for this case. I mean, of course, the circuit is going to be like this, but so there are 2 inverters here, and then this thing is V output high. Then what is this? I in prime. You know, if this one is this one,
It is 0.
it is 0. Yeah. So remember, it was the fan out limiting case was this, right? When output was high, it was limiting our fan out. So we found a solution to that. Okay. So this is the graphic. Maybe I should have drawn it like this. Oops. So 0.7 and then 0.8. 0.7 and 0.8. Okay. V output high, which is equal to VCC, and this one is V output low, which is equal to 0.2 volt. Okay, so what is noise margin low?
.5.
Yes, V input low minus V output low, which is equal to 0.5 volt. So not good. Okay, noise margin low is still problem here. How can we improve this? By shifting this there, right? So we input low can be, I mean, here it's 0.7 plus, if we put N times V diode, so maybe I should, you know, draw this with a different color here. N times V diode. By putting a diode here, okay, so N is 2 here, so N is 2 here. Then we input low can be shifted. So we input low is going to be here. It will be shifted to here. This will be maybe 2.1. If n is equal to 2. Okay. So it is possible to get this thing. So it's sharp, the transition. It's a good thing, you know, we like sharp transitions. So this is also shown in this graph. So by putting here, maybe either here or to this point, you know, 3 of them, let's say, extra 3. So this one is going to be 0.7 volt plus 3 times 0.7. This becomes what? 2.8 volt. That's too much maybe. And this is going to be 2.9 volt. Okay. So we noise margin low is going to be 2.8 minus 0.2 is going to be 2.6 volts. Noise margin high is going to be equal to 5 minus 2.9, so it's going to be 2.1 volt. Okay, so we can play with the noise margins by adding some extra elements here. So this value here is going to be obtained again. VCC 0.2 volts. This is V input low prime, and this will be V input high prime. Is that clear?
Yes.
So here, the assumption was that when this is off, when this thing is off, the current or resistance values RB and RC selected properly so that QN can go to saturation. So maybe here I should have said this, okay? Here we assumed that RB and RC are selected properly so that QN can go to SAT when Vin is larger than or equal to 0.9 volts. Is that okay? Because, you know, this is going to be the current, this is going to be the current. So when we calculate this, IC, and then this is going to be IB. Beta F times IB is larger than IC SAT. So IC SAT current. So what is IC SAT current? VCC minus 0.2 volt divided by RC. Okay, what is IB here? VCC minus 1.5 volt, assuming it's SAT, divided by RB. So that condition should be satisfied, and we know that it's satisfied typically. I mean, when we design it, we design accordingly. So if we don't give you numbers, you can assume that that goes to SAT, because we know that you know, for proper operation, we should do that anyway. Questions? So now the next item is the calculation of the fan out. For the fan out, we need to again look at two cases. One, output low case. And then the second one maybe is going to be for output high case. So when we say output high and low, that means this output, okay? One sensor, okay? So this is the output. Because in order to get that output low, we should give high voltage here. So we, you know, should be high so that we can obtain output low case. So here for both cases, we will be finding low maximum case and then N high maximum case, and then N max is going to be again minimum of these two, and low and high. Okay, so the idea is same. So we call this thing driving gates. These are loading gates, driven gates. So we can look at the low case here because this will be now actually determining the fan out. So what happens low case? Low case mean we apply here high voltage, high. Okay, so this is low. That's the case. The high needs to be applied here to get the low. So high means we apply here the highest voltage that we can give, which is VCC or 5 volts. Okay. So when we give here 5 volts, we know that this junction cannot turn on, so this will be off. But then we know that there's going to be enough current here. So this needs to remain at SAT, or this should be SAT. And then this is going to be 0.8 volts, and this is going to be 0.7 volts. Okay, so if this is SAT, the low means there's going to be 0.2 volts here. Okay, so if this is 0.2 volts, we know that this is on. Therefore, this is going to be 0.7. So this voltage is going to be 0.9 volts. Let's call it Vx prime. So if that one is 0.9 volt, this is going to be off, and this is going to be off, so that output can be VCC or high. Okay, so input is low, so this becomes high. Is that clear? So remember, I told you that this IB, and then this is IC. Maybe I should change the colors here, because I start talking about another subject here. Oops. Oh, I start to delete these. Okay, sorry. Now, this current is I base. This current is I collector. So for this to be in saturation, we know that beta forward I base should be larger than IC. So that's the case. So you know, for IC, there are two currents here. One is this current, IRC, and then also there are currents coming from these stages. We call them maybe these currents IN primes. So another IN prime, okay. So you know, we can just maybe draw the model here for convenience. So this is going to be your RB, this is VCC, and then this is 0.7 volt, V diode, B on voltage, and then we have here 0.8 volt, which is V collector, V base to emitter SAT voltage, and then V collector emitter SAT, and then RC, VCC. And then from the next gates, there's this one, RBX, VCC, and then 0.7 volt, VDAX. And then there will be one more, RBX, and then VDAX, and then maybe one more, okay. So and this voltage is 0.2 volt, and this current is going to be I base, and this current is going to be IC, and the IC will have two currents, IRC, and then this current, and then this is going to be N times I in prime. Okay, so from here we can find the limit, you know, because if more current comes here, this IC will start increasing. IC will start increasing, therefore our condition, what was our condition for proper operation? This should be in saturation. So for SAT, BF times I base should be larger than IC. At the worst case or maximum case, it will be equal to, but you know, this is what we should say. So beta F times I base. What is I base? VCC minus 0.7 minus 0.8 divided by RB. Should be larger than IC. What is IC? IRC, which is 5 minus 0.2 divided by RC, which is IRC, plus n times five minus 0.7 minus 0.2 divided by RBX. Okay, so from here can be determined. Okay, so that's the only unknown here. And it's going to be something smaller than. So if you just leave n alone, that's going to be your n max and low max. And low max can be determined. Okay, so since from the next gates, they keep, getting more and more current here, I am prime. So therefore current, this transistor cannot maybe become in saturation anymore. Okay, does it make sense? So the other case, let's do the other case also. The other case is simple. Output high case. Output high case means this point should be high, right? I mean, this point is going to be the high case. So in order to keep that high case, the input, we need to apply low. So low, if it is coming from a previous gate, it's going to be 0.2 volts. Okay. So if this one is 0.2 volts, let's find out how much current is going to go to this stage. Okay, so if there is any current to this stage, we call it IN prime and IN prime. So then those IN primes are going to be added, and then we'll create a drop on RC, correct? So V out, the minimum of V out can be allowed down to input high voltage. For this case, it's 0.8. So, but in any case, so if this is 0.2, we know that this one is going to be 0.9. So this will be off. This will be off. So cutoff means no current is coming from here. That means there's going to be, that needs to be current from here. But is it possible to have a current to diode in this direction?
Very small.
Yeah, it's negligible. So in fact, we call it 0. So what is the AX? I mean, we cannot have a current path here. So this will be, in fact, off. This will be off. So IM prime is going to be 0. I mean, I don't say it's IS. In fact, it's IS maybe, but it's 0. Okay. So therefore, V out is going to be VCC minus RC times IN primes times N. So this is going to be 0. So V out is going to be equal to VCC. Okay. Is there a limit? Since this is 0, N can be infinity, right? So it doesn't matter how many you connect, output will remain at high. So we say that N high max is infinity. I mean, don't come with projections like infinity times IS is going to be something, so whatever. Okay, don't say that. So there's no basically limit, or at least this doesn't affect. Okay, very, very high maybe. So for the output high case, then there is no basically limit, and therefore fan outs will be limited by the fan outs is limited and determined by the output low case. Okay, so that's it. We need to also calculate the power consumption. For the power consumption, we need to look again for the output high case and output low case. Power consumption, let's say this one is output high case. Let me do this, very quickly. Output high case, we need to find all the currents that's coming from this VCC. In fact, when you come to this, we already have calculated all the currents here. Okay, so for output high case, we know that input should be low. So typically we put here 0.2 volt because that's coming from the previous gate. And then this is output is VCC. And then this current is IRC is equal to 0. And then IRB is the determining thing. So therefore, VCC times IRB plus IRC, and this one is 0. Therefore, I need to calculate IRB, and IRB is, we already calculated VCC minus 0.8 minus 0.7 divided by RB. Okay, already calculated. Okay, and for the output low case, this should be low. That means this is in saturation. So we need to calculate this IRC and IRB. Okay, so in order to do this, this is 5 volts. So this one is off. Okay, so here, did I make a mistake here? low IRB was a mistake. Sorry. Wow. Nobody is warning me. This one, I mean, this one is off, right? This one is off. This one is on. This one is 0.9 volt. So this value would be equal to 0.9. Okay. And here, this will be off. And this will be 0.8. This will be 0.7. And then IRB is going to be 5 minus 0.8 minus 0.7 divided by RB. And then IRC is going to be 5 minus 0.2 volt divided by RC. Okay. So power dissipation for output low case is going to be VCC times IRB plus IRC. So this is not affected from fan out and is not really critical here. But here, no, it's okay. So average can be calculated from the average of these two. So I should stop here. Any questions?